So the idea is to use probabilistic methods to know more about the geometric structure, the subremanent structures of SU2C. So in the first part, I'm going to remind the subremanent structures to see and bring the model notions on. Then we'll talk about couplings in general, because I suppose that not everybody here is familiar with, of course. And then we'll give some examples, and then I will talk about successful coupling, which is a sort of coupling, what it can give to analysis, geometry, even other kind of probability, more mathematical fields than very applied ones, but what it can give, and which successful coupling we can find in SU2C, which are the main results of the paper. So first, what about SU2C? So yes, when you talk about supermanent structure, in general, you begin with Heisenberg group, but as Heisenberg group has been well explored, I will talk about SU2C. It will be the same structure. So it's a Lie group of matrices with the usual matricial product, and it's 2.2 times 2 complex coefficients. Group of matrices with unitary matrices with determinant 1. And so on this Lie group, to construct the supermanent structure, I will consider the polymatrices, which are here, which are part of the associative Lie algebra, and so which are part of the tangent space in the neutral point here, U2. So when you want to give a Riemannian structure, what you do is to define an inner product, inner product on the tangent space, to say that correctly. Here we won't do that, because the structure we will have with the Laplacian, that it will occur with this choice of polymatrices of basis of the Lie algebra. Will be generated, so we will consider only an horizontal space, and which is here two-dimensional, as SU2C is three-dimensional. And so on the horizontal space, we will define all inner product, and then we will define length of the curve and distance, just as we do in Riemannian manifolds. So here, to define the horizontal space, we just take the left invariant vector fields induced by the two here. And then for the inner product, we take the ones that give that make this family of vectors an orthonormal basis. And then we will so consider the horizontal curves, that are curves that take their tangent vectors in the horizontal space only. And we will define a length for these curves. And so define a distance of the infimum of the length of these curves, linking to 2 points of SU2C. So this really defines a distance. So this is because we have a good relation between the vector fields, the left invariant vector fields induced by this basis here. This is the so-called Hermander conditions, and thanks to that, we have this distance that is finite, and more, we have that SU2C is connected. So now we have a distance, and we will define an operator, just as we define the Laplace-Beltrami operator on a Riemannian manifold. The operator will be the sublation operator, which depends of x and y part. So this is not an elliptic operator, this is a subelliptic operator. This is an hyperelliptic operator. This means that when you take a function g and you look at Lg, if Lg is smooth, then g is smooth too. So this is a family of operator. And what we will do is define, this is also diffusion process. So we'll be able to define a stochastic diffusion process associated to that will be called Brownian notions. because Brownian motion on R2 is associated to the Laplacian operator, on Riemann manifold to the Laplace-Beltrami operator. So here it will be associated to the sub-Laplacian operator. And then we use the correspondence between Brownian motion and sub-Laplacian to obtain information about sub-Laplacian. So, yes, like that, Brownian motion we can do anything with. So we will have, we will use the so-called cylindrical coordinates on SU2C. So we can, yes, we can write every element of SU2C like that, with phi, theta, and z, which are in compact sets here, and x, y, which are the Pauli matrices I gave before. And with the cylindrical coordinates, we can compute the sub-Laplacian operator, which is like that. And what is quite interesting is that if you omit the path with z coordinates, you have the Laplace-Beltrami operator of the sphere, on the sphere S2, in cylindrical coordinates. So, with this sub-Laplacian operator written like that, we can take stochastic equations for the Brownian motions, which are like that. So I think I will not take a lot of time with that, and I will pass to the geometric local interpretation. So if I just look at the two first coordinates here, and I look at the cylinder, at the point it described on the sphere S2 in cylindrical coordinates. In fact, it is exactly a Brownian motion on the sphere. So this is the blue path I drew it here. And for the last coordinates here, we have, yes, a very, very good interpretation because it is a swept area, the area swept by the path here, so the red path here. So this is a sign swept area, so it's like negative or positive, but it is like this. And yes, as Z is chosen in a compact set, ZT is taken modulo 4P, it will be a little of importance for this what follows. So now, if I want to describe a Brownian motion in SU2C, I just have to describe a Brownian motion on the sphere, and the swept area is totally induced at the starting point, up to the starting point. So yes, I just have to study Brownian motion of the sphere, and that we can do. So yes, an important remark is that we have similar interpretations for two other sub-Riemann manifolds, which are the Heisenberg group. I talked about this before, and SL2R, which is also a matrix Lie group. For the first one, we can have the same decomposition in one, we call this an horizontal Brownian motion, xt, and a third coordinate zt, with xt, which is a Brownian motion this time on the flat plane, and zt, which is the swept area. So it's in R this time, but it's also is a swept area. And for SL2R, we have the same thing, but with a hyperbolic space. So we will be able to have a lot of things. And as there is good results on the Heisenberg group, the idea is to generalize these methods to SU2C and SL2R. Here I will really focus on SU2C because we don't have time. So now we go to the probabilistic part, really. Here we will define what is a couplings of Brownian motion. So to be very simple, I take 2 points, 2 starting points, and I will look at 2 Brownian motions starting from the starting points. And one I want to know is the joint law of BT and BT prime, which are my 2 Brownian motions. So I will look at the product the product law of these 2 Brownian motions. So now that I know that a Brownian motion on SU2C is a Brownian motion on the sphere and the swept area, if I want to define a coupling on SU2C, I just have to define a coupling on S2. So I will give example on S2. So on the plane it's quite easy because if you get on the plane, the Brownian motion decomposes like that with some bases that don't depend on the time in general, but can. And these are some Brownian motions in R2s, so independent Brownian motions. So when I'm on Riemann manifold, and here on S2, I can have a similar depiction of the Brownian motion with here vector fields. So here for the first vector fields, I will take the one that induce the geodesics joining xt and xt prime, which are my two Brownian motions. And for E1 prime, which will be the first part of the basis for this point here, I will take the parallel transport reduced vector. And I will just construct the two other vectors such that we have an orthonormal basis. So now I have this detection too. And I will be able to do iter calculus on this, adapt it to Riemannian manifolds, and then so to compute the distance between the two Brownian motions, for example. So the examples, I promised some examples. So yes, then I have to do couples. So I have my two processes, and what I will do is take U1 here, V1 here, and first ID I will take the same. So V2, V2. It will be the same vector, doesn't vector, I would say. I take same, and I will have something which is like that. So because of the curvature, the distance between the two Brownian motions will be decreasing. In reality, it will be a deterministic process. So and it will tend to 0 at the limit. Another example will be the reflection mirror coupling. So this time I take U1 and V1 opposite. I take the same two Brownian motions for the other direction. So I will go like this, and with same direction with these two vector space. And I will have something which have a symmetry here. And more important, this this reflection coupling will be what we call successful. So the idea is that in an almost surely finite time, the Brownian motions will meet. Yeah. So and we also know estimations of the distribution of this first coupling time. That, as I will call it. So I will pass. So now I want to do successful couplings on SU2C. So I get the exact definition of successful coupling. So I take two Brownian motions in SU2C. I take two starting points, and I look at the first coupling time, which is the first time where the horizontal Brownian motion, that is my Brownian motion on the sphere, has met, and at the same time, I want that the swept area to be equal. So why do I look at that? Motivations. So the idea would be to study in general this the distribution, in fact, of data, and this quantity that I will call the coupling rate, which is so the first time the probability that the coupling don't occur before time t here. And I can have first probabilistic results as here comparisons of the probability of the distribution of the two Brownian motions on SU2C at time t. So here it's with total variation distance. And I can say that it is hyperbolic by this quantity. It's really simple to show. Another thing that I can have is relations about heat semigroup. So here is a heat semigroup, so it's a semigroup associated to my sublapation, and I can see that it is also given by the mean of the index of my process at time t. So I can show very simple also that the difference of the two heat semigroup at time at point xz and x prime z is measure bounded by these coupling rates for all Brownian motions starting from these 2 points. So, and then the other application will be to study harmonic functions. So, as you all know, I suppose, in R2, when you consider harmonic bounding functions, it is always constant. It is not true on all Riemannian manifolds, for example, the parabolic plane. But Wang proved in 2002 that on a Riemannian manifold with Ricci curvature bounded below, we have successful coupling of Brownian motion if and only if harmonic bounding functions are constant. So, yes, there is a real link, and it is not surprising. We can have similar results with something like that. And for example, as there is no, as this condition here, this Liouville type property is not satisfied for hyperbolic plane, it is not, there is no successful coupling on the hyperbolic plane, as an example. So now, I go back to my successful coupling in SU2C. We will not have time, I think, to explain how we do that, but this is a generation of the strategy of the Heisenberg group from Kendall. And I show that there exists a successful coupling of Brownian motion on SU2C, so two Brownian motions starting from a point and meeting at an almost refinite times. Here, I don't have an idea how the coupling rate is in progress, but I don't have an idea for the moment. And yeah, what is interesting here is that normally on SU2C, the swept area is considered modulo 4p, and here with this strategy, I can just consider the swept area in R, and I still have successful coupling. So no link in reality with SU2C, but maybe something useful for other applications. Another thing is that here I call that co-adaptive coupling. So what is co-adaptive coupling? The examples I gave before were co-adaptive coupling. So the idea of co-adaptive coupling is that I won't look at the future of one of the two curves to construct my Brownian motions. This is not always the case. The coupling I will give just after won't be the same. But yeah, in probabilistic terms, it's clear that the processes are adapted to the same filtration. And if co-adaptive coupling easy to simulate, in general, the coupling rate is not optimal and is difficult to compute. Here, I don't have for the moment. Then, so another strategy to have a successful Brownian motion, successful coupling of Brownian motion on SU2C. So yes, what I forgot is that the first theorem was a generalization from Kendall, which did that on the Heisenberg group, so the plan. So it was very much easier. If you want to begin with something, I suggest you begin with it. Yes, so the second one is a generalization of the work from Banerjee, Gordina, and Mariano, even if it was a little more difficult to generalize to SU2C. So here, we suppose that the Brownian motion, the horizontal Brownian motion, so the Brownian motion of the sphere, are starting from the same point. So I just have the swept areas that are not equals. So what I can show is that I can have a successful coupling with that. And that's more, the coupling rate is exponentially decreasing, and that's more, I can get a modulus, an upper bound with the starting points, so the difference of the starting points for the swept area, Z and Z prime. So here, the idea will be to say, yeah, I fix a time t, deterministic, and what I want is that at each time t, the Brownian motion of the sphere just mitigate. So this is using Brownian bridges, and this is why we have here a non-quadratic coupling, because to have the Brownian motion that meet exactly at time deterministic t, I will have to go see in the future of one of the two curves to have something. So, and the idea will be that during my coupling, I will make a time t, and I will try to work on the swept area during this coupling to have a probability that the swept area will be, the difference of the swept area will be equal to 0 exactly at time t, a probability that is more than 0. So when I will repeat the experiment, there is a moment where I will have a success, even if there is some independence condition to satisfy. But this is a high. Yeah, this theorem is also true for SL2R. So I remind SL2R, the Brownian motion on the hyperbolic plan. But of course, I can't have a successful coupling on SL2R if I don't have that, because I can't make a Brownian motion meeting on SL2R. So if there is whatever is doing the swept area, it won't meet. As the Brownian motion, the result Brownian motion won't meet, I won't have successful coupling on SL2R. So, but using the coupling I get here, this one was successful in S2. So what I will do is use this reflection coupling to make the Brownian motion starting from different points on the sphere, and they will meet on an emotionally finite time, more than they will meet on with the coupling time, coupling rate that is exponentially decreasing. And so, combining these results and this theorem, I will have a successful coupling on SU2C, and I will have also a new pair bonded depending on the counterparatory distance, so this distance on SU2C between the two starting points. So this is quite interesting because with it I can have results here. I can power bond with an exponential decrease rate, and the counterparatory distance of the two starting points, and I can have results just like harmonic functions, Brownian harmonic functions are constant. So this is all the results I will try to obtain now. It won't take a long time, but it has to take time. So yes, thank you very much. I think that I won't have more time, but it is finished. So I hope I will have you will have appreciated this talk and open your mind about what couplings of Brownian motions can give to geometry. Thank you very much.
Questions? Remarks?
Do you think certain kind of extension for higher dimensional situation?
Yes. In the Heisenberg group case, where we consider the Brownian motion on the plane and the swept area, it has been generalized by Kendall. So the idea was to consider all the n-dimensional Brownian motions on N, and all the swept area that are reduced. And it proves that, yes, there were a successful coupling just like this one.
But what is the area in that case?
What?
I mean, the area has to do with the dimension, right? Or no?
The swept area has to do with the first coordinates.
Oh, just the first coordinates.
Yes, we have n-dimensional Brownian motions, and then
the last
n
coordinate.
N plus one, the half
Okay.
n plus one coordinates. Then. So yes, this is not really easy, and I think that maybe we could obtain something similar on with this coupling, because when you are using Brownian bridges and couplings of Brownian bridges, the idea is to take a decomposition of the Brownian bridges, a sort of Fourier decomposition of Brownian bridges, and so you will have the model of the decomposition that are Gaussian. So as I have a number of Gaussians, maybe I can play here we couple just one Gaussian, we take all the Gaussian equal except the first one. Maybe dealing with not taking just the first one equal, but not taking just the first one different, but making others, maybe we can have something similar. And for SU2C, yeah, to the case of the sphere, I didn't look at something more general.
Maybe a 7.
I think that yeah, but yeah, I think that maybe the first one could be okay, but it's not exactly the same method to do that in high dimension. So maybe, but I'm not so sure. So I don't want to, but maybe. I think that if you're interested in that, yes, you will have maybe this one, or maybe this is a more recent paper from Kendall. This is for Heisenberg. Yeah. Most of the couplings we have a supernormal manifold as for Heisenberg.
More questions? If not, let's thank Magali again.